Good afternoon, everyone. On behalf of the NCESS Art Science Forum, I extend a very warm welcome to our respected director, distinguished scientists, research scholars, students, and all attendees to this National Space Day lecture. We are truly honored to welcome our chief guest, Professor Dipankar Banerjee, Director, IIST. National Space Day is observed to celebrate India's historic achievement on 23rd August 2023, the day Chandrayaan-3 successfully soft-landed on the lunar surface, an achievement that placed India among the leading spacefaring nations of the world. The day stands as a symbol of India's scientific excellence, technological innovation, and the spirit of exploration that continues to inspire generations. To formally begin the proceedings, I would now like to invite our Director, Sir, Professor 𝗓𝗲𝗄𝗲, to deliver the welcome address and to introduce our chief guest.
To all of you, and hearty welcome to Professor Dipankar Banerjee, Director of IIST, on this very special occasion. And I also welcome my colleagues, my research scholars, and all guests, and also many of those who are attending this function or this special program online in virtual mode. Hearty welcome to all of you. As Neha has said, 23rd of August, the government has announced it as a National Space Day, and because it happened to be on Saturday, we are celebrating it today, so the more people can participate in that aspect. Human being is always fascinated by things which he or she cannot access, and two things which come to my mind is inner air and also outer space. And outer space exploration always remained one of the greatest adventures of all time, since time immemorial. Space exploration is a source of inspiration for science and technology across the world, and India's journey in space, led by ISRO and allied institutions, including IIST, stand as a shining example of how vision, perseverance, and scientific excellence can propel a nation onto a global platform and recognition. It's no exaggeration to state today before you that space science and exploration has revolutionized human lives by understanding so many things. To start with monsoons, fish productivity in the oceans, predicting natural disasters like cyclones, tsunamis, mineral exploration, telecommunication, anthropogenic urban flood monitoring, and practically everything. I was chatting with Professor Banerjee. It's influencing us in every sense, at every angle, and playing also very prominent role in geopolitics, including in wars and conflicts. Today is also the day to remember some of the renowned Indian scientists, space scientists and astronomers who contributed to the space science. I start with 𝗂𝗲𝗄𝗲, who understood in those days before Christ that the earth rotates. He supported the heliocentric theory where sun is at the center of this solar system, and he explained very elegantly the solar and lunar eclipses. Brahmagupta and Valiamala, who built on the models of 𝗂𝗲𝗄𝗲 and explained the planetary motions with absolute accuracy and precision. The modern Indian space science owes greatly to extraordinary individuals who are also best of friends among themselves, Dr. 𝗗𝗁𝗲𝗄𝗲 and Dr. Homi Jahangir, who had the vision and imagination to conceive the space program in the country just when we got independence, and we were in all sorts of troubles or problems and not much funding was there, but they tried to convince, and they were very successful in convincing the powers at that time that we need to have a space program, and that's where today where we are. And Thiruvananthapuram is a place, it's actually the space cradle of India, because the first rocket was launched at Pamba, not far from here, where Dr. Sarabhai and Baba, they were all there. And the 𝗓𝗏 Space Center, now IIST, are all located here. So it's very fitting that the National Space Day should be celebrated in much more grandeur by the institutes located in Trivandrum. Of course, the legacy of the space program in the later years was carried out by such eminent scientists who are household names, such as Professor Satish Dhawan, Professor U.R. Rao, Professor Dr. APJ Abdul Kalam, who worked for many years at Vikram Sarabhai Center, Professor Kasturi Rangan, and many others, which made it possible that the country's remarkable ascent to the global space science, where it occupies among the one of the leading countries in the world. Today is also the day, in my opinion, to celebrate the endeavor of astronauts and the erstwhile cosmonauts, such as Yuri Gagarin, the first man to enter the space, Neil Armstrong, our own Kalpana Chawla, Rakesh Sharma, Subhanshu Shukla, and many others who pushed the limits of human knowledge and dared to ask what is there outside, with a lot of dareness and spirit of adventurism. At NCESS, National Center of Earth Science Studies, I should tell very briefly with our chief guest that ours is a 47 years old institution, started in 1978 as a state government body under Kerala State Science and Technology Board, and it was also created by a visionary, Dr. 𝗓𝗏 who served as Director General of GSI. Then upon invitation of the state government, he started this center. And the uniqueness of our institute is, it is concerned with all aspects of Earth system science. You know, today we talk about Earth, ocean, atmosphere, planetary, and everything, environment in one breath. And it was 𝗓𝗏 who conceived that long back, much before the term Earth system science itself has come into existence in 78. And in 2014, Ministry of Earth Science has taken our institute into its fold, and we are part of MOES. So at NCESS, our core strength lies in solid Earth, but we share an inseparable link with space science. And both our Earth and space are both same sides, two sides of the same coin. And we are closely associated with ISRO in many aspects. For example, our members are in the task team of ISRO, who are in this Chandrayaan-4 sampling procedure. Some of our members are involved in it. And we are also working a lot on planetary materials like meteorites. Our scientists and I, myself included, we work on them. And we have an atmospheric science division and marine science division and environmental hydrology group, where remote sensing geospatial technology is extensively used in monitoring and also in observations. And we also work a lot on space-Earth interactions here. So as we celebrate Space Day today, let us remember that the quest to explore space is not just about exploring distant planets and stars. It's also understanding our own planet in a much better way. Unless we have a holistic perspective, we can't understand how Earth itself has evolved. So every mission, every experiment, and every discovery made in space science helps us to reflect on Earth's origin, evolution, and future sustainability. And I'm sure that the collaborations with institutes like IIST and other ISRO institutes and ISERS and educational institutes will open up new areas where we can venture into, not only in Earth and space science, but also in a lot of integration or transdisciplinary sciences. I think on 10th of next month, 5 institutes, central government institutes in Trivandrum, we are all getting together, including IIST. We are going to sign an historic MOU so that all of us can work on same platform, and all their labs will be open to students and all from other institutes. So once again, I profusely thank Professor Banerjee. He's extremely busy. He was there along with Professor or Minister the other day on Space Day thing, and he was at Bangalore. He could find time to come over here. And let us take today's celebration as a motivation to aim higher, explore further, and to contribute meaningfully to our country's national science progress. Thank you and Jai Hind. And it's also my pleasant duty to introduce formally Professor Dipankar Banerjee, who is the Vice Chancellor of the IIST. He joined on 14th October 2024. He is basically an astrophysicist with a bachelor's degree in physics from the famed St. Xavier's College, Calcutta, and he also has a master's degree in theoretical physics from University of Calcutta. He has obtained his PhD from Indian Institute of Astrophysics at Bangalore, and he completed 2 postdocs from reputed institutes in Europe. And he served as the director of a very renowned institution, IIST, called Aryabhatta Research Institute of Observational Science, located at the picture city of Nainital in 2019 to 24. And he's also serving as a senior professor in Indian Institute of Astrophysics. So Professor Banerjee's main area of interest, as you can see from the picture, is the sun and the solar atmosphere. His work involves theoretical and numerical modeling using data from the ground and space-based instruments, and his work has enriched our understanding of the sun and its impact on the space weather. He served as the co-chair of Science Working Group of the famous Aditya mission. You all know Aditya is the first dedicated Indian mission to study the sun, launched by the ISRO in September 2023. He is also involved in NASA's Punch mission. He is a fellow of the Indian Academy of Science, fellow of the National Academy of Science. He is a fellow of the Royal Astronomical Society, and currently is also the president of Astronomical Society of India, which speaks volumes of his scientific contributions. Professor Banerjee has more than 150 peer review publications, around 4,000 citations in international and national journals, and is currently supervising 5 PhDs and successfully guided 15 students so far for their PhDs. And apart from his scientific career, Professor Banerjee has interest in various other activities. I understand that he is trained in Hindustani vocal as a part of Bengali theatre group, 𝗓𝗲𝗏, and regularly performs in plays, participating in national and international theatre festivals. And Professor Banerjee's love for science and just for life are infectious, and we can all see and feel for ourselves. With these few words, I heartily welcome Professor Banerjee here, and I invite him to deliver this special lecture. Thank you.
You can probably energize me. Yeah, I'm audible, yeah. Thank you, 𝗗𝗲𝗺𝗲, for this. Maybe I should turn off this one. Yeah, is better? Yeah. For this kind invitation. I see you have already started my presentation because there were some slides on the sun. And thanks for your introduction. I guess she's from eastern part of India because she pronounced my name perfectly. So because you don't expect in South to have such perfect pronunciation for Dipankar Banerjee. So I'm really glad to be here, and it's a really first time for me to this campus. I'm also very happy that a lot of young scientists are there. I was just chatting with him that you're a young institute with a lot of young faculties. So today my intention would be to keep this. Is this audio better, or I use a? There is a bit of a bit of noise. So yeah. So so that way I would like to keep it very informal. And please feel free to stop me. There is a bit of noise. I am not liking it. Maybe I should just use this. As you heard that. Yeah, hello. Yeah, as you heard, I work on stage, so we don't like too much noise. And we normally do not use too many microphones also. So in Bengali, we call it amic. It has double meaning. You don't need a mic, or it could be very polite. So my intention would be to give you a glimpse of our institute also, because although we are in Trivandrum, it appears that we all do not know about each other that well, about the activities, scientific and training activities. So I thought I will use this opportunity to give you a quick tour to our campus, and will invite you to visit our campus anytime you would like to, because this kind of interactions and exchanges are very important, because today science is multidisciplinary. And you will see that even in IIST we have a good overlap. Of course, Ramarao is here today. I'm thankful for that, because we do have a few faculties whose core area of interest very much overlaps with the field that you are doing here. So first statement is Aditya L1 is a indigenously developed 𝗗𝗲𝗺𝗲 perfect example. And there are many, many institutions within academic fraternity and ISRO centers have been involved in this mission. So this is also a very good example of how different ISRO centers have worked with pure academic research institute like yours. Because I also come from a parent institute called Indian Institute of Astrophysics, where the youngest individuals are the PhD students. At II also we don't have an undergraduate or postgraduate program. So that kind of institute focuses on very focused science domain. ISRO, of course, helps us with all instrument building and integration and so on. So in this first slide, you see many logos of academic institutions, starting from TIF or PRLI, ISC, all these different ISRs. So just to highlight that it is really a multi-institutional effort, and I will not be able to properly acknowledge every individuals in this. So on behalf of the scientific organizing working group, I am here today. So a brief tour of IIST. That's our temple inside the institute, namely the library. That's the campus at Valiamala. You will be making a small little tour here. It's quite a nice campus because we are on the way to the 𝗗𝗺𝗲. So you can take a break and drop by before going for a picnic to 𝗗𝗺𝗲. That's also possible. We have 11 hostels filled with PhD scholars. We still do not have a housing for our faculties or even the Vice Chancellor. But so our priorities are always with the students. So it's a very vibrant, academic, residential, campus, because majority of our students are actually on campus that way. We do have good sophisticated labs now. So this is a lab which is building all the small space, satellite payloads. So our undergraduate students in this lab build these payloads, and every 6 months we get an opportunity on the POEM platform to take those payloads, and we have a ground station in IIST. The students after dinner, they can go and just download the data and work on it. So this kind of space exposure, experiential learning experience doesn't exist anywhere in Asia. This is all JPL model, but we are really fortunate to have that system. And of course, this is Department of Space's own institute, fully funded. So that way we get these privileges or platforms in ISRO missions as well. We do have primarily the BTech programs in aerospace, EC or avionics, and this year we have started a new BTech course in computer science and data science, because data science is becoming everywhere. So it's important to have a combination of computer science expertise with the handle of machine learning and AI and things like that. We also have a dual degree program whereby these BTech students who are from engineering physics, they can choose either a MTech or a MS in the 5th year. Whatever they choose in the 4th and 5th year curriculum decides on that dual degree program. This is also a very, very successful program because, engineering physics is something, as you heard, I'm mostly from physics background. So engineering physics is something which some of the IITs started. And then this also is a very successful program, and majority of these dual degree, students are now scientists at the different ISRO centers. I mean, you name it, any mission, you will find our students actually playing a major role there. We also have 16 odd master's program. You see, I'm just giving this probably, for younger people here, it doesn't make direct impact, but please do convey this to your, family members or juniors or youngsters, that such opportunities exist in India.
And earlier, the BTech program was, of course, still today, the BTech entry is only through IIT JEE Advanced, along with the IITs. But the master's program entry is through Standard Gate. And then PhD program is also through NET or, or GATE. So that's the qualification criteria for PhD, but then there is an interview. So this is very similar to any other research institute. And if you see, we have 410 PhD candidates now. Of course, within that, there are 150 odd are ISRO scientists. They are doing their PhD while on the job. The rest of the about 250 plus are now regular PhD students with fully, paid scholarship. So that, and if you look at the academic departments, we have, as I indicated, the two major engineering departments, but we have physics, chemistry, maths, earth and space sciences as a department. Initially started from physics, but then later on, because of the nature of requirement and all that, earth and space science is a department. So you have one of the faculties here, Ramarao, but we do have other faculties also who are working in the domain of geospatial and all that. And as you very nicely portrayed at the beginning itself, how important it is to look at the sun and earth system also as a coupled system. You cannot actually do any science in isolation now. So earth is, after all, earth and its atmosphere, our presence is all because of the presence of sun at an appropriate distance away. So what is happening in the sun or any effect, what you are studying here is all the source is a sun. So if you do not understand the sun and solar variability, you will not understand the earth's variability also. So whether it is long term and short term. So I will actually impress on you how important it is to study not only the short term, also the long term behavior, which dictates our climate, basically. So that way, this multidisciplinarity, and then, of course, we have humanities department also for a holistic, training of the students. And that's the typical number of the strength of students and faculty we have. Of course, we are here today for the National Space Day, held annually on 23rd August to commemorate the Chandrayaan's successful landing near the moon's south pole in August 23rd. How India celebrates flagship event at Bharat Mandapam in New Delhi with sessions and exhibits. So just 𝗓𝗶𝗺 mentioned that I was there till Saturday. Before Saturday, we also had a national beat 2.0. After 10 years, actually, that happened. And all the secretaries were also there and different ministries. So the main theme of that national meet was that now the approach is completely different. Earlier, say, ISRO was planning what all missions to be done, what all, at different phases, what kind of technology demonstration should be there. Now it is driven other way. It is user-driven. So 50 plus user, ministries were called. And ministries are now asked, what is it, how you want to use the space for your own purpose. As 𝗓𝗶𝗺 pointed out, whether it is a, blue economy, whether you want the fisheries department or even the Ministry of External Affairs were there. I was saying what the Ministry of External Affairs will do here in this, meet. So every ministry is actually saying what way the science or the space data can be used, or space platform can be used. So it appears as everybody is using data from either for geospatial requirement or for, or your science requirement or for, or national sovereignty requirement. So, of course, Ministry of Defense is working very, very close. And the Sindoor thing, where 24 satellites were used. 24 satellites were full-time used for that operation. So we do have such capabilities, such independence now. So that is also very, very important how well we are, able to do it on ourselves. I don't know whether you are aware. I heard, many a times this story that why did we lose so much in our Kargil war? Apparently, the Americans did not share the GPS. So the soldiers were all got isolated. There were no communications. And that time, the government decided that we should have our own GPS system. So that's how all this Navic and all this. It's the only thing, we take a little while. We still use the Google map. We are not using Bhuvan platform. So I think Ramarao has the role to play. how to make these, softwares, user-friendly so that one will start using our own systems. You see, China has done that, right? You go to China, they don't use Facebook, they don't use Google. They have their every, similar platforms, and they're very efficient actually. Baiju is very, very good actually. I've used it. So I think there is a part which we are still lacking. So that's the kind of way we sort of celebrate this ISRO-led programs, including Space on Wheels and Space tutors, and activities across the country such as lectures, workshops, and quizzes. So today, I hope I also contributed a little way and interacting with you in this session with this. So since my subject is sun, I have chosen to focus on sun today for rest of my talk. So why sun? In fact, this is a question, it came when I joined for my PhD program. I had no clue about astronomy, no clue about astronomy. In fact, in my interview at IIST, I told that please don't ask me anything about stars because I'm from Calcutta, and Calcutta you can't see sky with stars. I said, no, they will not ask you anything about stars. It all starts with the black body radiation, and then you get into the physics of a black body, which is a star. So at the end of the day, it's all the basic sciences which is linked for any astrophysical objects which you study. So sun is a normal star. It is in the middle stage of its stellar evolution. It is of course a spatial star because on which we can resolve the spatial scale. So you will see from my movies and pictures and so on how much details on the different layers of the sun in the atmosphere surface we are able to see today. Because most of the other astronomical objects, we study them as a point object because we really do not have such greater details on that those objects. Of course, it is a special star because it provides almost all the energy to the Earth. Our existence is because of the presence of sun. And also it provides a unique laboratory to learn about various branches of physics. I mean, if I normally give a talk to physics students, I spend some substantial amount of time after this slide and demonstrate whether you name it, whether you name it atomic physics, molecular physics, nuclear physics, particle physics, I can give you hundreds of research problems just on the sun. Because the conditions what we have in the sun is not achievable almost in terrestrial laboratory environment. Of course, 99.9% of the universe is in the plasma state. Sun is also in the plasma state. So if you want to study plasma physics, again, that experiment you cannot run in the laboratory at all. I mean, it's very hard to, you build a tokamak after spending hundreds of crores with just a maximum size of this room. Whereas the sunspots, I will show you, is a natural tokamak of 5,000 kilometers size. So if you really want to study the physics in those conditions, you have to actually, connect or look at the observations from astrophysical objects, and sun really provides a good key in this. Sun's internal structure, of course, we can't see inside the sun, but we have plenty of information about indirectly about the interior part through nuclear physics experiments, through particle physics experiment, and a field called helioseismology. This is again related with Earth seismology. Since you are experts of Earth seismology here, exactly the same technique is used for observations of acoustic oscillations on the surface of the sun. And then we infer the properties of interior of the sun by studying helioseismology. Technique is, that's why it's called helioseismology, because it's just the same seismology technique applied to the sun, Helios. So right in the core, where hydrogen is getting converted into helium by the PP chain reaction, then we have energy propagated about 30% inside through radiative process, and the photons do travel and they interact with each other because the density is very high. It takes almost millions of years for a photon to finally escape because it's a random walk which is happening inside. Then the last 30% inside is convective, and energy is transported by convection. It's like a boiling of soup. And we see direct manifestation of the convection on the surface, because this is the image of the surface. You see the cellular kind of structures, and those structures are nothing but, if you boil a soup, you will see at the end, when the convection is fully set up, you see these kind of cellular pattern, and that's what we see on the surface pictures. And you also see these kind of locations where the sort of, it appears dark as compared to the surrounding, and these are the locations where strong presence of magnetic field, and these are called the sunspots. So I will say more about it. And then in the atmosphere again, there are many different structures with different time and so on. So now I will come to again a quick look at the different variability what we see in the sun. So here you see one example where these are the locations where sunspots are there underneath. So this is an image taken from Solar Dynamic Observatory at extreme ultraviolet. We are probing a plasma temperature of 0.8 million Kelvin, which is a plasma pertaining to some heights about 2,000 kilometers in the atmosphere of the sun from the surface. Normally, these regions you cannot see it from the ground because they are emitting either in shorter wavelength, in extreme ultraviolet or in X-rays and so on. So we need to go to space, but we can one way see this during the total solar eclipse. So that's one other very interesting period over which historically we have only seen the corona, the outer inner atmosphere of the sun. So here, these are the locations where magnetic field is present. There are sunspots. Sunspots always comes in pair. There will be north and the south, and they will be connected. So these structures are called coronal loops, and they are there for sometimes hours and days, but then they become unstable and they explode. And after the explosion happens, so you see the it's a bit of slow response. So these locations, if I can run this movie here, and you will see that there, some explosion happens, material are thrown into interplanetary space, some material goes back, and these are giving rise to the solar storms. There is a physical mechanism which is happening inside. They're called magnetic reconnection. Essentially, there are a lot of magnetic field connectivity, and these magnetic connectivity, they interact with each other. Normally, magnetic field repels each other. They don't like to, connect. But if you force them to connect, then the connectivity changes after this reconnection point, and huge amount of energy is released. Whatever magnetic energy is confined with these huge magnetic structures, they are released in the form of heat and kinetic energy. So this is one kind of variability of the time scales of hours to days gives rise to solar storms. There is another kind of variability which is depicted here, and I think 𝗓𝗶𝗺 knows it very well, is the variability of the sunspot number for last, say, 400 years, which is plotted here. So clearly one direct observation is there are period over which you have lots of sunspots, and which is called solar maxima, and there are periods over you will find that there are hardly few sunspots or no sunspot at all. So these are called the solar minima. Typically, the periodicity is about 11 years, but then the amplitudes are also not always same. There are even last 100 years, you see, during 1950s, there was a solar cycle which was very, very active, very dynamic. And we don't know really because, that time there was no space program at all. How many satellites were damaged during those times because of this number of solar storms must have been very, very, very large. So that period, what really went on, we don't know. Of course, we know a period over which this happened, 1650 to 1700, there were hardly any sunspots recorded. What was the effect? The Volga River was frozen for 40 years. The people were skating in the Thames River in London. So it was extremely cold. So there is a direct influence of, sun being not magnetically so active and our climate. And it lasted for almost 30, 40 years. So this is also related to the mini ice age. So now, of course, with other proxies and so on, what people have done people have tried to, look back in the millennia time scale, which 𝗓𝗶𝗺 also does. And there you have discovered that there have been at least 22 odd, solar mini ice ages. And so many IISts are now directly, related with the solar, total energy output. And total energy output, it appears, also has an influence whether, there were sunspots or not. So this is also called the Maunder minima, because Maunder first discovered this. There is another thing which is depicted here. These two vertical lines shows the period over which 𝗓𝗂𝗂𝗂 actually observed the sunspot number, and he predicted that the sun undergoes a 11-year solar cycle. So this is again the visionary views about 1.5 almost, not even 3 solar cycle. We say, if you want to detect a periodicity, at least 3 periods should be there. But these guys had such a intuitive mind that he could say, oh, there seems to be a solar cycle. So solar cycle was named after 𝗓𝗂𝗂𝗂, and he hardly had, not even not even full 2 cycles for that matter. So this is called the long-term variability, which has a very big implication in terms of our climate, called the space climate, which has again big importance in our Earth atmospheric environment and all that. So I would like to again really emphasize that Earth's atmospheric conditions or local conditions, even climate or weather-wise if you want, there is an influence of what is happening in the sun. So the variability of different time scale studying is very, very important. And that is, I'm just trying to pitch here, why did we think about a solar mission in the first place? I will show at the end probably a few examples of what, observations we are getting from Aditya and what all instruments we built and so on, for what reason. I'm just trying to impress on you that it is important to understand the variability in the sun. And that's the area which is directly linked with the kind of studies what you do here as well. Of course, there are many more observations. Again, I see another case of a huge explosion in the solar atmosphere as recorded by the Solar Dynamic Observatory. Now, this is a closer view. Then if you want to see the full sun, that also is possible to see. But now then ejecta goes out of the sun, you need to track them. So how do you track them? We use an instrument called coronagraph. We block the solar disk light, and then there's different size of coronagraphs you can make, and you can follow the propagation of these structures. Because these structures are eventually traveling, some of them are coming towards Earth, so it interacts with Earth's magnetosphere, and that has a lot of effects on our day-to-day behavior as well. So it is important to, sort of study the properties of these ejecta, when they're coming, how much energy they are carrying, what sort of particles they are carrying, what sort of magnetic field they are carrying, because that is eventually going to interact with our space asset, that's one thing, and also our Earth's magnetosphere, because we are here because of Earth's magnetosphere, otherwise our existence also would not have been there. We know that this is again another big question in context of the astrophysics is now we have discovered 5,000 other planets, 5,000 plus other planets. But is there life possibility there in any other planet? Crucially depends on where the central star is, what is the state of the central star, whether that planet has magnetic field. All these questions are, directly linked. So it is very important to understand. This is a movie from Parker Solar Probe. This is again probably the most sophisticated and highly technologically challenged space missions in today from NASA. For Lagrange 1 mission, we have traveled 1.5 million kilometers from Earth. That's quite big. But that's only 1% of the distance between Sun and Earth. Parker has traveled already 70%. So, of course, they're so much closer to the Sun, they can't look at the Sun at all. They're looking away from the Sun. Even the material science research, what has been incorporated in Parker is the top of that. Any material science applications which has happened in the Parker Solar Probe all led to the Nature-like publications, because the heat shield what is there is also a composite which the mankind never built before. So all these new stuff can be tested in a space environment also for the first time. So that is again another probably good reason why do we go to space. because you can't really test those things in normal laboratory conditions anyway. So here I'm just showing that when such a huge coronal mass ejection or this ejector comes out of the sun, what is the environment look like? And I'm sure if Elon Musk wants to do a space tourism, he would like to pass through that storm. And even if it is, then we have to protect these rich guys. So means you have to actually predict when such a storm is going to happen. So that leads to a new field which has emerged in recent times. It's called the space weather. It is just not your terrestrial weather. It is the space weather which is influencing our life actually. It is just not, I mean, the storm in the ocean affects the fisherman a big way and the people living in the coast. But anybody in the space and whatever space technology we are using, for example, we all use ionosphere for all communication system. Ionosphere gets damaged when such a storm comes, right? You can imagine if such a storm comes, eventually it will interact with the ionosphere. The ionospheric density is going to be completely disturbed for certain number of hours, and so your communication is gone. Satellites can, of course, momentarily lose their positions and their systems. It can also completely get destroyed, depending on where the impact is, how much energy that particular magnetic cloud is carrying. I mean, we are planning our own International Space Station, and Mr. Shukla, if he wants to do some work outside with a suit and all that, if such a storm hits, it's gone. So it is very important for many, many different aspects. Of course, these energetic particles, I mean, you are all earth scientists, so that they normally cannot penetrate to the lower in altitude. Well, Thiruvananthapuram, it will probably not hit that easily because of the magnetosphere, but they do enter from the polar regions. We see the auroras and all that because of all these. We are going from Delhi to New York nowadays. We don't go via Europe. We go by a polar route. So we are actually exposing ourselves completely when we take such flights. In fact, it is not a statutory warning. I do not know how it is still happening. For a pregnant woman, it is actually very, very harmful. The kind of dosage our body gets when such a huge solar storm happens is actually considerable. People only talk about X-ray machines and all that, but that is much more highly energetic particles actually, cosmic rays and other, gamma rays. I mean, all kinds of particles are coming. And if you take a polar route, there is a exposure. So, of course, they do penetrate for high latitude locations like Canada, Alaska, and other places where they directly hit the transformer electrical systems. There are blackouts actually. It has happened. In fact, in Canada, in the extreme winter, apparently because of a solar storm, the power grid system failed. The metros also were stopped for several hours. The insurance companies had to pay a claim of something around 10 billion. So now insurance companies are actually taking this as a service from solar physicists that, please tell us that we have to give statutory warning and so on. After that, if something happens, you need not pay. Of course, everybody has their own intentions. So I'm just trying to give an impression that whether it is telecommunication, GPS network, air traffic, satellite health, lifetime, astronaut safety, electric power grids, oil pipeline. It's an oil pipeline, all their mechanisms are very, very crucially depend on the GPS. If your GPS gets disturbed, you are going to be, vastly misled. So this is not any fancy science anymore. It is actually a service to the globe we have to provide by, handling the understanding. So what it demands is you have to understand why such solar storm happens, when it is likely to happen, and if it happens, not all the storms are same. No two storms are actually same. So is it possible to predict that storm's arrival time at different points in the space, and the impact analysis, and then mitigation plan? So it's actually really, really comprehensive, understanding and modeling efforts. There are hardcore computer simulations requirement, hardcore, observational, requirements. So it's really a multidisciplinary, comprehensive new science domain which has emerged. And it all emerged in last, a decade or a half. And in fact, in the Western world, they are taking it very seriously. It is not into anymore in NSF. I mean, in the US, it is done by other agencies. Air Force is doing, predictions. They have their own data centers to analyze. So now, only very recently now, I have been called for, DRDO and Air Force and all that. So our Air Force people are actually coming to IIST for a 2-week training, because they need to understand what is space weather. And of course, there is another related things are called the space situational awareness. All the satellites are there, and then there are thousands of dead satellites. What's happening with them? They are actually 𝗗𝗲 in the space. So that also is going to affect our system. So we can track them, the astronomers can track them, and plan for mitigations and so on. So that's the background. Let me now come to our own mission called Aditya, which we launched from PSLV C57 last.
जहाँ पर पूरे vehicle को assemble किया जाता है.
These are the visuals from the clean room of the spacecraft preparation facility. This is the Aditya L1 spacecraft being prepared and ensconced into a protective container where the environment is controlled and the temperature is controlled, the cleanliness is controlled. At the vehicle assembly building, again, there is a clean room provision to safely integrate it to the rocket, and then the heat shield halves are closed. Now the vehicle is fully ready to be moved to the launch pad, which is about 900 meters away. This is PSL. The mission intends to place the spacecraft in 235 by 19,500 kilometers orbit with an inclination of 19.2 degrees. The total mission duration will...
And you can go to the public gallery. Yeah.
अब हम प्रमोशन से 22 मिनट की दूरी पर हैं. आदित्य L1 सूर्य का अध्ययन 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Yeah, these are anxious moments.
Plus 5 seconds.
Gone through this.
Lift off normal. Pure tracking. PT tracking.
Magnificent.
So I will skip some of this. So in this, particular launch, there were different stages. You normally, probably some of you observe some of the PSLV or JSLV launch. Depending on how far you have to go, where you have to go and all that, there are different stages. And this was one occasion where the satellite separation happened almost after an hour. And some of us were actually interviewed for the first time just to kill the time. So did not know what to do with this 40 minutes commentary. So they called some of us about usefulness of the mission and all that. We did actually quite a clever way this particular mission. Indians are always some way find out alternative ways. When you do not have a very heavy rocket, then how do you reach a longer destination? Then apply our crude logic of 𝗓𝗓𝗄𝗲 game, or if you remember the slingshot mechanism, you just put a stone and then tie it in a rope and then and make few rounds and then throw it. It goes further rather than trying to throw it straight away. So exactly the same mechanisms is actually applied here as well. So we had 5 Earth-centered orbit, and then there was a long 3 months cruise phase, and then the insertion. And Lagrange 1 is a very unique location where once you reach there, then there is a force balance. Essentially, the force between the satellite and the Earth balances the force between the satellite and the sun. So if the sun at distance is about, say, 100 unit, and sun is 99 times heavier than Earth, so that ratio also is effectively there. Because to be in a sort of a highly elliptical orbit, you need certain centripetal force, and that force is provided by this force balance. So you're not actually using much fuel at all. So once you are there, you can live there for, tens of years. In fact, the 𝗂𝗲 was launched in 95, it is still orbiting. All the instruments are not fully functional, but the satellite is still alive. So it depends on how much, because occasionally once in 1 or 2 months, you have to do a little bit of thruster and then correct that, because, the calculations are based on, say 3-body system or 4-body system, but it is eventually n-body, simulations which you require. So time to time you have to make a little bit of course correction by applying the thruster, but continuously you do not need any, any fuel at all. And being at L1, before anything reaches Earth, it has to pass through. So you have a possibility of doing a combination of remote sensing and in situ measurement. So I will again run a small little movie for instruments.
The Aditya L1 mission carries a suite of 7 scientific payloads.
So let's stop the movie itself.
The Aditya L1 mission carries a suite of 7 scientific payloads to carry out systematic study of the Sun. The Visible Emission Line Coronagraph, VELC, studies the solar corona and dynamics of coronal mass ejections. The Solar Ultraviolet Imaging Telescope, SUIT payload, images the solar disk in near ultraviolet and also measures the solar irradiance variations. The Aditya Solar Wind Particle Experiment, aspects and plasma analyzer package for Aditya. Pamba payloads study the solar wind and energetic ions, as well as their energy distribution. The Solar Low Energy X-ray Spectrometer, 𝗂𝗲𝗃𝗃, and the High Energy L1 Orbiting X-ray Spectrometer, 𝗂𝗃𝗃, study the X-ray flares from Sun over a wide energy range. The magnetometer payload is intended to measure the interplanetary magnetic field at the L1 point. The science payloads of Aditya L1 are indigenously developed by different laboratories in the country. VELC is developed at the Indian Institute of Astrophysics, Bengaluru, suit instrument at Inter-University Center for Astronomy and Astrophysics, Pune. Aspects instrument at Physical Research Laboratory, Ahmedabad. Pamba payload at Space Physics Laboratory, Vikram Sarabhai Space Center, Thiruvananthapuram. 𝗂𝗲𝗃𝗃 and 𝗂𝗃𝗃 payloads at 𝗂𝗏 Satellite Center, Bengaluru, and the magnetometer payload at the Laboratory for Electro-Optic Systems, URSC.
So as I pointed out that we are around Lagrange 1, and you see, I don't have to explain too much of you about the Earth's magnetospheric structure, the nighttime versus the daytime, because of the solar wind as well, as I think all of you are aware. Along with the, these huge ejecta, we also have the solar wind. So this is again another very challenging thing to work out the real arrival time of the CMEs, because solar wind is not a background which is always uniform. Solar wind itself is very much asymmetric. It has a dependency on the solar cycle. So depending on the phase of the solar cycle, there are solar wind days. So it's similarly, I give normally this experiment, I throw a stone in the river or a flow of water. So a lot depends on not the injection of the stone alone, it also depends on the flow in the background. So here that is another very important problem for the prediction models, how to do a computationally really model of the solar wind along with the CME propagation, because they are interacting with each other, and depending on the CME speed, whether it is slow or intermediate or fast, you have a completely different scenario, and the formation of the shock and all these effect what you see is very different. So for that reason, we have a combination of remote sensing instrument, this solar ultraviolet imaging telescope. Primarily we are looking at the chromosphere. This is the middle atmospheric thing. between the photosphere, which is the visible surface, and the corona, you have this chromosphere. So this near UV instrument is primarily looking at very close to the source region. So I would like to point out that in Aditya, what we are trying to do is we are focusing on the source region of these storms, whether what sort of dynamic sizes and what kind of lifetime it goes through, and when such ejecta happens, whether we can capture the initial acceleration part of that, because there are a number of satellites which is looking at the big picture of the CMEs and so on. Because always, from India particularly, when you are trying to do it, rather than doing just copying that what others are doing, because our sometimes the technical abilities in terms of the new instrument, we are building it for the first time, will not have the best resolution and so on. So why do that? So first thing always have to be that what others do not have. So, and can you build those part within our system, and then it complements to the global scenario or the understanding. So I think that is a bigger exercise which some of us were involved for last 20 years. And then we do have 2 X-ray spectrometers. Helios is looking at really the strong flares, which emits really high energy particles as well. And then the Solex looks at flares of smaller sizes, which is happening all the time throughout the entire phase of the solar cycle. Whereas the highest energy flares are most likely happening only when the sun is very active, because they are directly related with the active regions and so on. And as in situ instruments, we have this Pamba instrument, which is built very close to your office here in SPL. In VSSC, Aspects was built in PRL. If Anil is coming, then probably he will also give you some new results from Aspects, which I'm not showing today. Then magnetometer is also built at LEOS in Bangalore. Just a very quick glimpse. As I indicated, we have a corona graph which is blocking the solar disk very close to that. And we are able to capture these structures and their evolution. And this is still a lot of cleaning is required. I'm just sharing some early results, because you see there are still detector issues, a lot of calibrations and all that. But still we are able to capture the plasma through a ionized line, which is representative of 1 million K plasma. And these are spectral imaging. This is not, and this is done by a little bit of complicated way. We have a multi-slit experiment, which is also first time done from space. It was done from the ground, but not from the space. And it creates a image. So the slit position is there, and then you sort of move the slit to get every single locations. We have a full spectrum, and from full spectrum, what happens is you can do some diagnostics in terms of its temperature, density, and all that. It's just not pretty images. It has all the physics parameters inbuilt to this. That will allow you to really see the changes in those structures, their physical conditions, physical parameters, for understanding the physics of it, just not images alone. That's the sort of beauty of it, and such thing doesn't exist anywhere else from any other platform. Then we have this near UV instrument, which was primarily started from IUCAA in Pune. These are filter images. These are not spectroscopic, but these are filter images. We are capturing the sunspot, then surrounding regions are called the plages. The other regions normally called quiet sun, but nothing is actually quiet in the sun. But these are historical names. And then with these different filters, we are able to probe different layers of the atmosphere. So you see that, when you take images with different filters, basically they are probing different plasma atmosphere, and that will give you a comprehensive picture of a multi-layered thing. So that again in the near UV was not there from the space platform. So we chose the near UV filters for the first time, and this has also a very big implication in terms of our climate, because most of the times in the past people have looked at the EUV. Of course, people look at the total solar radiance, that is called the irradiance thing, which has impact on our climate. But the near UV irradiance studies for a long term has not been done. There are theoretical predictions that the overall total intensity changes are only 0.1%, but the near UV changes could be, within that, could be as high as 20%. So near UV is very much, influencing our ozone layer changes and all that, which has again other warming effects and all that. So this part has a lot of implication in terms of the, atmospheric studies as well. So I'm from an astronomy background. It's only the, IIG people are somewhat involved in this. So this is again another domain I think, the atmospheric scientists guys should actually, get in, because our interest has been always in the sun. But now I see, as I was indicating, it is a coupled system. Unless you, look at all these and comprehensively each other causal and source and, effect analysis, you are actually having only a half-cooked stories. Again, as I mentioned, from these suit instrument, we are able to capture the early phase of this ejecta. You see, this is very close to this, lower atmosphere, and then, I mean, one can say that, if you compare with this and the NASA, the big pictures, your resolution is still not up to the mark, this, that. But I would, we are able to publish in Astrophysical Journal letters and all that, simply because these wavelengths have not been seen. So the point is that you have to do multi-wavelength studies. Either look for X-ray, look for UV, look for near UV, look for infrared. So we have an infrared camera also. So these new sort of eyes are giving you a slightly newer picture, and which helps into a comprehensive understanding. But for that, you also need to observe from other satellites. You cannot do it in isolation. So that is the other aspect which I will finally talk about. This is just a glimpse of the low energy X-ray spectrometer, which is working in this range. We are only looking at sun as a star. That means, integrated flux only we are measuring. So here, what is shown here is this big spikes corresponds to flares, big flares, and it's for comparison, we have shown you the 𝗂𝗲 curve. 𝗂𝗲s are the best American satellites. If you want to do first time, always you have to compare with the best ones and show that how good your correlation is. So it shows, we are doing pretty well. The cross calibrations are pretty good. And this all happened actually 14 December 23. This was even before the insertion. So this is again another new story about ISRO. See, we were, the insertion at the L1 happened in January 24. And this cruise phase is long, so we are all keeping quiet. Once we are there, then only we'll be asked to open the telescopes and all that. But ISRO was so confident that, once we reach close to Lagrange 1 and so on, they said, oh, if you like, you can open the telescope. I said, wow, this was not known. So we started our operation, science operations. Actually, some of it was all called, test operations. But we have the quality of data in the test phase, and really top journal publications are coming from that test phase of the data. Of course, it takes a while to calibrate it and all that, but we have done that. Last May, this was very unusual. Within a week, there were so many X-class flares. So X-class flares are the strongest flares, which sometimes happens once in a year. And, sun was, probably helping us, because of course, we are in the peak stage of solar activity. That did give us so many extra flares. Enormous amount of data is there with us. In fact, Minister also announced that 10 terabytes of data is in the public domain now. This is again another big aspect of open data policy and all that which we are bringing in. So when such flare happens during that week, this is the record from the magnetometer. So of course, those are looking remotely, the X-ray fluxes and all that. But then when this magnetic cloud, huge cloud, comes to Lagrange and hits our satellite, in situ we are measuring this. So you have all the three components also, Bx, By, Bz. That also allows you to get a three-dimensional reconstruction of the big structure. Because it's just not you are just getting one count. You're also from the difference timing and so on, you can reconstruct the magnetic cloud itself which is coming. Because earlier these possibilities were also not there. We were just seeing, okay, some magnetic, things have come. Of course, that gives you a validation that has come to this particular position, it has taken that long. Then when it reaches Earth, what is the impact it can make? But now we have even a three-dimensional picture of it, which will allow you to see the extent of the damage, the total energy content of this. So it's one more level of, sophistication which you can do. For all this, we need many more users. So Aditya L1 support cell is actually at Nainital, and I was fortunate that I was given that task when I was heading that institute from ISRO. And now my younger colleagues are continuing that work. We do conduct workshops. Every 3 months almost training workshops are done. And earlier we were giving them test data, now they're given Aditya's data. And they're trained with the data analysis tools and all that. We are also conducting teachers training workshop, so that the teachers can get trained and they can subsequently train people. So please, if anybody is interested in using Aditya data, all the data are hosted at IIST. Anybody can access the data. They have to fill up some forms, and some guidelines are there for usage of the data and all that. But it's all available globally. Anybody can use it. This is last few slides. Want to again point out that we started all this after quite a while. Our space program was dedicated for, of course, communications, surveillance, and other. Science is a luxury, it comes last. But we are fortunate that now time has come, we can afford this. We had dedicated astronomy missions in the form of AstroSat, which is celebrating its 10 years of operation in space. Aditya was initially conceived as a low Earth orbit, one payload mission. That was the approval. But after Mangalayan's success, ISRO modified that. And in fact, Professor 𝗂𝗲 was instrumental. He decided that we will have a much more challenging mission in the form of L1 mission. And then, of course, when it was announced, we scientists are always greedy. So we'll say, oh, we are going that far. It's a full-fledged, big, satellite can be accommodated. So why not some more instruments? So from 1, it became 7. So that's a big leap, actually. So only thing what I was trying to highlight here is there are, in the heliophysics systems observatory, there are 20 operating missions with 27 satellites from different agencies, whether it is NASA, ESA, JAXA, the Russians or or even the French. We started a bit late, but we started with a bang. And I think we have already gone quite far, and we can be at shoulder to shoulder in terms of the sophistication of a observatory class mission as well. Because as I indicated, small satellite missions, microsatellites and all that, science also are limited. But when you have an observatory class mission with multi-wavelength capability, your scope is really, really much more. So I think the younger generation are in a golden age now in space sciences in India, I would say. Even, the rest of the world is coming to us. We heard about NISR launch. This is again another example. Last December, Proba 3, this is a technology demonstration from European Space Agency. It was launched from our satellite PSLV. So they found, because ESA had some issues with their timelines and all that, their launch vehicles were not available. I was told that they contacted SpaceX also, but it was not so much attractive or whatever financial terms. So the reliability factor, again, is also a big thing. Even the agency like ESA, if they want to launch from our platform, means we have proved some credibility. So what is this mission? Again, it is a very fascinating technology demonstration. This is 2 satellites. They were clubbed together. This is very similar to our SpaceX experiment where the docking thing is done. So they were docked together, and in space, they are separated by 150 meters in formation flight. And the first satellite is blocking the solar disk light. And you see here clearly that this is the umbra, the shadow of the solar disk. which falls into the second satellite, and we are imaging the corona, creating a total solar eclipse situation artificially in space by formation flying. And the precision with which these two satellites have to maintain their separation is few centimeters. So how it is not possible to be done by, it's completely done autonomously on board by laser tomography. So one satellite sends a laser signal, and then it's a, really the next generation sophistication of positioning two objects in space by completely independently. So two satellites, there are no ground command or anything. It just initiates that and they maintain it for 6 hours every orbit. So this is a technology demonstration mission, Proba 3, and since they are also looking very, similar target, and you see this is the first image from their coronagraph, and they have the similar spectral line of iron. So we have the spectroscopic information, they have the spectral imaging information. So now we are going to work together very closely to see all these structures which you see, much more detailed in terms of imaging here. But now we will be able to do the diagnostic part from our own coronagraph as well. So I think this example where I thought I will share with you how important it is to collaborate, how important it is to look at all options which is available globally, and then do the science rather than doing it in isolation. Because your overall output will be much better when you have a complementarity, when you have this kind of larger communication. So I think experimental science do need collaborations. I think when we were young and all that, a lot of criticism, oh, how many authors are there in your paper? What is your contribution? This, that. Of course, you have to highlight your contribution, but this level of science is not possible to be done in isolation. You really need to work as a team. And I see it that also, it excites me more than doing work in isolation. And since I work with a lot of students, students also get much more benefited rather than just interacting with me alone and learning only limited things. So I think it's been a lifetime experience for me to be part of this mission and being present in the control center, seeing the launch from 𝗓𝗗𝗄𝗏. And I hope the next generation will have many such opportunities for future missions. And thank you for your attention. This is a picture from my previous locations in the Himalayas. This is taken from this mobile camera from our observatory. So you're most welcome to visit either that place or this place anytime you like. Thank you for your attention. Yeah, I'll be really happy to answer questions, because if you don't ask me questions, I will feel that, I have not conveyed anything. Yes, ma'am. Yeah. So there are actually 5 Lagrange points. I was just looking whether I have that slide here somewhere, and I probably have not included that. So they're called, no, I don't have this slide here. 5 Lagrange points. So L1 is the location which is between Sun-Earth line and only 1% distance, 1.5 million kilometers from Earth. There is something called L5 and L4, which are in the sides. In fact, since you asked the question, we already planned for a L5 mission. In fact, if Professor 𝗂𝗏 would have been around, probably we would have already an approved L5 mission now. But of course, reaching L5 is quite challenging. It will take years to reach there. But apparently, we have capability of going. So nobody has gone to L5 globally. European Space Agency has now approved mission for L5, because one advantage of here is Sun, here is Earth, and L1 is here. L5 is here. So and the Sun is also rotating about its own axis. So what we see from Earth, if you are in L5, you will be seeing it actually 4 or 5 days even before. So it's a very, very important point to have observation from L5. The L4 is here. So now the Koreans have started talking about, because Europeans are already reached, or plan to reach L5. And L3 is of course behind sun. That's again a fantastic point, because behind sun what is happening we don't know at all. After 13 days, because sun takes about 27 days for one full rotation. After 13 days only we see what is there behind the sun. So it's a fantastic point, but the problem is if something is there behind sun, we don't have any telemetry. It will happen in future, because L3 will talk to L4 or L5, and then we will transmit. So it will be not direct, but so these are all our things there. Since you asked this question, we have satellites in L2, not us. So 𝗓𝗲, the James Webb telescope, which is now the best, largest telescope for doing astronomy from space, is at L2. L2 is behind Earth. So that's not good for solar observation, because Earth will block the view. In fact, they've gone to L2 because to protect their infrared systems from heat and so on. So they need a shadow of Earth. So L2 is a perfect location for looking at the night sky, deep sky and so on. We are planning to go to L2 as well. So that approval is just waiting for Commission's approval. And IIST is the PI institution for that L2 mission for science. So I hope you will hear more about it in coming. At least within my tenure, I want the L2 mission to be approved and going. Yeah. Yeah. Mm-hmm.
Seismology.
Yeah.
I forgot his name. He's from
𝗗𝗲 Yeah.
Now, are these sunstorms which you shown and we study are manifestations of some type of quakes?
Yeah, a good point. So these are called sun quakes. So what 𝗗𝗲 studies is the continuous oscillation, because sun also oscillates with millions of modes. So many stars, solar-like stars, they are actually pulsators also. And since they pulsate, but that oscillation is very, very tiny, few meters per second, and we observe them from the Doppler shift motions and study them and all that. So those quakes are regular quakes. It's basically a resonator. Sun is a resonator because 30% inside is convection, no? So the acoustic wave travels inside, they get reflected because of the dispersion properties, same principle, and then come back, and those acoustic modes, they superpose with each other, and then from the superposition you can observe them. But when such a big flare happens, that can also propagate as a sound wave, huge sound wave, global wave. So those are called sun quakes. And that also is observed. I mean, there are all these seismology techniques are used for doing some diagnostic of the sun quakes and all that. And so sun quakes are actually quite a good, and traditionally, these used to be called as the white light flares. Like, there has to be very big that, even the small telescopes and all that, people have seen it in the historical times.
Okay.
And they gave rise to sun quakes. So we do observe them, time to time.
Okay. And the magnetism in the earth is due to its dynamo within.
Yeah.
And is there a different in the sun?
Absolutely. So the sun is definitely, the magnetic field is because of the dynamo action. And now we understand the dynamo is operating at the base of the convection zone. And sun, there is one more important element, is sun is not rotating as a uniform body. So it rotates differentially. The equator rotates faster than the pole. So I did not go into that particular domain. So the dynamo which is in the sun is called the alpha omega dynamo. So there are two effects. One is the differential rotation, and the other is the convection. And in the case of the earth, we have a solid crust. So it is a dynamo action, but the equations are different. So of course, the rotation and the internal structure properties, that is the crucial elements for a dynamo action. So for the stellar dynamo, it is different than the planetary dynamo. And that's why the time scales are also very different. So we don't know when I did not talk about it, the solar dynamo also flips polarity. So the north, so polarity reversal happens every 11 years. So that's why the magnetic cycle of the sun is actually 22 years. Because every 11 years, polarity reversal happens. But for the Earth, we don't know when the polarity reversal will happen or happen.
But in Earth also it happened a number of times.
Yeah, so
But not in this time scale, but in a much
larger
longer.
time scale.
Yeah, yeah.
And in fact, there is still large, error bars in those calculations.
true.
I know you have also a lot of interest. There are, people say that there are indications that the reversal has started in the Earth. So there are some new reports which is saying that we are seeing signatures of, Earth's, polarity reversal.
Okay.
But they're, controversial. So.
Now, we have a branch called paleomagnetism.
Right.
We have we used to have a very renowned scientist here. He retired, but his student is around.
Very
so,
good.
So, I mean,
So
we
these
have
will be
facil-
good things, I mean, you also should come down. I mean, in the arts department also has some. We do not have a, magnetism, expertise. Mostly in the atmospheric dynamics and geospatial domains. We have more.
Rajesh.
Yeah.
He's a geoscientist. He has a lot of collaboration. with
Right.
our institute.
Right. Rajesh has some overlap. Right.
Any?
Yeah. Question.
CME orientation in space is very much important to know the effect which is going to happen on Earth. So, Aditya L1 is the satellite. What is the instrument we use to know that?
Yeah, a good one, very good point. So what he is referring to is, I did not elaborate on that. See, Earth also has its magnetic field. So the orientation of this magnetic cloud which is coming, so the coronal mass ejections, when it travels in the interplanetary space, we refer to them as magnetic cloud or ICMEs, interstellar CMEs. The orientation of the magnetic field of the CME with reference to Earth's magnetic field interaction is crucial for understanding their impact. They will be geoeffective based on their orientation and all that. So that orientation, if you try to get an estimate very close to the sun, it need not remain the same by all the time it travels. So the magnetometer is actually the main instrument which is helping us. And as I was giving you indication, since we have a three-dimensional Bx, By, Bz, we should be, whether it is, Bz component is there or not, that should be able to get from there. So all the magnetometers which are now coming and in fact, so has had ACE has a magnetometer. So that also are giving us these indications about the BZ component, because as you rightly pointed out, that's crucial for the geo-effectiveness of that CME interaction. So the magnetometer is a crucial instrument for that. Yeah, there's a question here. No further questions? No, please don't feel shy. I still have time. Because I don't have time to go back to institute. Yeah, we can do that. Yeah, sure, I will be happy to do that. Yeah. Okay. Yeah.
Thank you, sir, for such an enlightening lecture. Now, I would like to request our director, sir, for giving a memento as a token of our appreciation to our chief guest. Thank you, sir. As we conclude, I extend my gratitude to our director, sir, our chief guest, Professor Banerjee, and all the participants, both, who were there in online mode and who are present here also. Thank you all.